Hello everyone. I welcome you all to the PACK-NIN webinar series. The PACK-NIN project is funded by Marie Curie grant. And I am Sudha Isekimutu. I am a Marie Curie fellow working at Renew Center of Excellence at Slovenia. So this PACK-NIN webinar is organized in a different webinar series. And the first webinar focuses on different field based on lignin chemistry and packaging and biorefinery topics, different biorefinery topics. So today our speaker is Dr. Mika Sipponen. I will introduce him. He's an assistant professor and he leads the Sustainable Material Chemistry Research Group in the Department of Materials and Environmental Chemistry at Stockholm University, Sweden. And Dr. Sipponen, he obtained his doctoral degree from Aalto University, Finland, and he worked as a research scientist at VTT industry. And after his research scientist position, he worked as a postdoctoral researcher with well-known professors in a biorefinery field, like Professor Monica Sterberg from Aalto University and Professor Claudia Costrini from University of Rome, Italy, and also Professor Yoshiko from Shinsu University, Japan. And his research expertise includes biomass processing and applied biochemistry, and more recently, more focusedly on lignin-based functional material development, mostly on lignin nanoparticle related research. So today his presentation on lignin nanoparticles as functional pillars in composite materials. So I really pleased to welcome Dr. Mika Sipponen for this presentation. And you can share the screen now.
Thank you, Sudha, for the very kind introduction, and of course, thank you for organizing this seminar series. And on the behalf of course, in the Renew, it's a very great initiative. So it's very nice to be here today. And as Sudha basically introduced, I will focus today on lignin nanoparticles research. But I will connect it to the composite materials, which is of course the topic of Sudha's Marie Curie project as well. So I will proceed with my presentation. So I will just want to show a little outline and try to get the laser pointer here. Maybe I don't need it. Okay, so I just want to give a brief introduction first to the topic. Let's say for our interest to the field, why my group is motivated to work on lignin-based materials. Then particularly lignin nanoparticles that we have focused in recent years. Why so, and what can we do with them? And then go to the topic of today. So basically the composite materials that employ these nanoscale particles. And finally, to summarize the presentation. So the big picture of our motivation for lignin research is that in industry there's about 70 million tons of lignin available worldwide. So every year, this is a massive amount. Of course, only part of that is isolated for products and materials. But this could be significantly increased, and we have more like a demand supply problem here in terms of we don't have enough end users and applications that could take all of this lignin that is available. But lignin as such is a very interesting biomaterial. It's, as you may well know, it's about 1/4 to 1/3 of the wood and plant biomass, and it's made of aromatic chemicals which form very heterogeneous polymers, which is also polydispersed, and this is called lignin. So the idea here is that we want to, of course, develop circular bio-based materials, and we see that lignin nanoparticles could be one, let's say, a building block that enables production of these advanced materials like composite materials which would be ideally also biodegradable. So this circle would be complete. What comes to composite materials, the research when it's linked to lignin nanoparticles is relatively young, but often it's motivated by the cost side of the lignin particles. So if these are considered as fillers or reinforcers, they can be compared to, let's say, inorganic or organic particles, which are often more expensive than lignin. The price of lignin is very difficult to say specifically. This could be about 600 euros per ton, but this depends on the purity and the producer. What comes to the composites, also the performance has been the very key driver for the research. So this performance relates to different functionality or mechanical performance and so forth. And let's say only recently some works have studied the safety and environmental aspects a bit more in detail. However, these are also very important. So what are these lignin nanoparticles then? So these are basically spherical particles. They have been under recent years a few different technologies to produce them. One of them is this solvent exchange or nanoprecipitation method, which produces particles in the size range of from 50 to 500 nanometers in diameter. They are hydrophilic from the surfaces, so they are charged and stable in water in a pretty broad pH range, excluding the extreme acidic and alkaline conditions. They can be produced in a relatively high yield, and this is a non-covalent synthesis, so we don't need any chemical functionalizations. Then these particle dispersions can be concentrated to relatively high concentrations. However, this is dependent on the particle size and other properties which need to be controlled pretty carefully. As the product, these are very amphiphilic. They are good adsorbents for different, let's say, materials like enzymes, polymers, and small molecules. The process is in brief just shown here in this schematic. So it involves first a dissolution step and then the precipitation by removing the solvent or adding water into the solution. And then finally, of course, the organic solvent can be removed and recycled, and we get the final particulate product. So as I said, these particles are very hydrophilic from the surfaces, and the chemicals, let's say, functionalities have been identified recently by liquid state NMR, or dispersion state NMR technique, which is a very nice advancement in the field. But what I want to highlight here is that, first of all, the hydrophobic nature of lignin has been very controversial. It's very regular to read papers that say that lignin is aromatic, so it equals that it's a hydrophobic. But this is not, of course, true, at least for the isolated lignins. And what comes to these particles, they have been also shown to have very interesting behavior when they are heated up in dry state. So in this paper, which I show this image on the right, we found that if you take the 0.0, so the whole paper was about making stabilized particles by adding epoxy crosslinker into the particles. But if we just take the regular particles, so 0.8% of this crosslinker, we see that by heating up these particles, the water contact angle of the particle films increases quite significantly from about less than 20 degrees to up to something like 100. So they actually become hydrophobic. So this is one, let's say, consideration for the composites. So even though they are hydrophilic, these particles might even still be compatible for hydrophobic matrices. So here I want to visit a bit, let's say, put all of the works here. Some recent works on the particle composites. So I will just sum up this, that there have been works with, let's say, renewable composites, especially the nanocellulose, nano-lignin composites have been studied recently with very nice results, but also synthetic polymers like PVA, polyurethane, and our work on polystyrene and butyl methacrylate and also polymethacrylate. So here I want to just say that it seems that there is a threshold for the concentration or the weight percentage of the particles that can be added to the composites. And there seems to be an, let's say, a sweet spot, often about 10 to 15 weight percent, where we, let's say, reach the highest mechanical properties, at least in the tensile testing. And this is probably because of this interfacial saturation in the polymer composite system. But anyway, even though there have been some works, I think there's lots of room for new systems, like, let's say, PLA is one of the interesting polymers, but why not also polyolefins and other synthetic plastics? Here I want to remind that, yes, there's about 300 million tons of plastics is every year produced. So this is something that we should tackle and also replace some of those plastics by renewable materials. Coming to this slide, I want to just present how we managed to produce some polystyrene, for example, polystyrene lignin particle composites. I don't go into details, but the idea was that we made an in situ polymerization using an emulsion polymerization system. And these emulsions were stabilized by the lignin particles that were coated with enzymes. And here this enabled us to use different non-water soluble hydrophobic monomers for the polymerization. And basically, this combined the best of the two worlds. So the lignin the particles were very good for the emulsion stabilization, but also then they formed very nice polymers with good properties. And basically it was a kind of side invention here that we found that we can actually increase the lignin particle concentration quite significantly to make these composite materials. So that we focused in this follow-up paper that was recently published, and we took polystyrene and PBMA as the let's say focused polymeric systems that were in this case produced by free radical polymerization. And what we found is that, well, this is the photo, SEM photo of the emulsion particle that has been polymerized. So this latex particle, which is coated by the nanoparticles on the shell, and this formed basically very nice material that could be used for the melt processing. So forming these composite films and specimens was really straightforward. We just simply dry the emulsion and then melt it and melt cast it into composite shapes. Here the key was that even though we were melting this material, there was no clear separation of the phases. So the lignin particles remained very finely dispersed in the matrices. And basically this resulted in an excellent mechanical behavior. I summarize it here. So even in this case, we found that there was sweet spot at 15 weight percent of the lignin particles in the system, but even with higher amounts up to about 30%, we can still actually exceed the performance of the pure polymer, especially in the case of the PBMA. And in case of the polystyrene, we found that the increase in the tensile properties was basically highest that it has been reported. So why is the what is the reason for this? We believe it is like a dynamic sacrificial bonds that are forming. So these are covalent linkages that form between the polymers and the particles. So when we have the polymer matrix, these particles act as kind of nanospacers, which enable the stretching of the material and then also make it more elastic, while also giving some improvement in the strength. And one more dimension to this is that we can of course be critical that is it a good idea to combine a synthetic plastic with renewable organic material? So how can this be reused or recycled? Well, we cannot give the full answer, but we at least can give a partial answer to this question. And we studied that after we have broken this specimen with 10% of the lignin particles, it can be actually reprocessed by simply melting it again. And this could be more like a reprocessable material before the eventual disposing off at the end of the lifetime. And of course, when we have lignin, it's usually that what we get is the properties and functionality is what is normal to lignin. So we can get the UV barrier properties and the antioxidant activity, which can actually be very important for composites, so to protect them for aging and other such deterioration effects. But to summarize today's presentation, I just want to highlight a few things. First of all, we think that the lignin particles are very promising functional fillers and not restricted to the polymeric systems that have been studied so far, but there are many new opportunities. And as I just mentioned, UV absorbance, antioxidant activity, and other barrier properties such as gas and moisture barriers are kind of obvious functionalities that arise from lignin, but this can be, of course, very, very beneficial. Then for the future studies, I would say the biodegradation is one of the key questions that should be addressed, as well as recycling safety from the perspective of packaging, for example, food, migrative substances, and other such issues, but also from the environment, and more work is required. And of course, I'm very happy that we have now this collaboration between InnoRenew and my group at Stockholm University, and I think this will be a nice few years to come to work jointly. And to conclude, I want to just thank my excellent group for the hard work and all the external funders. And of course, I thank again Sudha for bringing this nicely together, and also Dr. David De Valence from InnoRenew and the whole staff at InnoRenew. So yeah, thank you again, and I would be very happy for any discussion and questions.
Thank you, Mika, for the very nice presentation. And now, floor is open for questions. So already we received one question from chat from Dr. Veerapandiyan. What about degradation of the lignin nanoparticle after coupling with polymers like styrene and butyl methacrylate, and how those additional polymers impact the degradation?
Yeah, this is an excellent question, and unfortunately, we don't have an excellent answer at this moment. But what we can predict is that the lignin will be equally biodegradable as its, let's say, the building or the starting material lignin is, because we don't introduce any covalent modification. That's the base case. So I would expect that these particles can probably, to some extent, improve the biodegradation of these fossil polymers, but anyway, they don't solve the, let's say, very slow biodegradation or even non-existent biodegradation in some cases. So it's I think we need to develop more a concept for recycling and separation of the components.
Okay. So next question, very informative talk from Professor Mika. Does your group work on carbon nanoparticle derived from lignin nanoparticles?
Yes, so thanks for this question. This is very hot topic, obviously, making carbonized materials. So the honest answer is that at the moment we don't work, but we have some collaborations which we are addressing this this field. So we had a recent paper on carbonized lignin particles in ACS Nano. This was collaboration with the group of Orlando Rojas from UBC and Aalto University in Finland. UBC in Canada, and I think this is very promising field. So let's put it this way: we have some strong interest in this area.
Yeah, we also had the same interest, like producing carbon nanoparticles from lignin, because in our group, Dr. David has a specialization on carbonization kind of stuff from wood biomass. So we are also planning to prepare some kind of nanoparticles, but we applied for a proposal and waiting for the funding. So in case if we get something, we can share the knowledge with based on lignin.
Yeah, I think that would be lovely, and I see
Yeah.
that also industry is now getting activated in this regard. So there's public information, for example, from Stora Enso, who is doing has invested already or made an investment decision to make a pilot plant for kraft lignin carbonization to make carbon materials. So yes, I think it's very hot topic and hopefully the future.
I think the second question also related to this electronic application of biocarbon from lignin. So we can expect in a near future more based on a lignin biocarbon. Yes. So is there any more question from? If you want to ask, you can unmute your phone or your microphone and ask directly. If anyone has any question. Okay. I have one question related to bonding characteristics. Like you said, with the lignin nanoparticle, you observed kind of compatibility with the composite material. And somewhere you mentioned also covalent bonding. I don't understand. This is mean the lignin nanoparticle is directly making the covalent bonding without any modification with the composite material.
Do you refer to this slide or?
Yeah. This
yeah.
one.
So here sorry, I was maybe not clear. I meant non-covalent. So
okay, sorry.
these are the weak interactions. So
okay.
yes, so we don't think that there are any important covalent bonds in place, but therefore that's why we can explain that this become more flexible and also have this dynamic, let's say, feature.
Okay. Thank you. Okay, is there any more question?
Professor Mika, can I ask you a question?
Yes, thank you.
Professor, my name is Avinash, and I'm a PhD student at Mahatma Gandhi University in India. And I work on cellulose-based materials for electronic applications. So as I asked you in the question, are you looking into any applications on like sensors or supercapacitors or battery electrodes based on lignin, carbon, and cellulose composites?
Yeah, thank you, Avinash, for this question. Obviously, this is a very strong field, at least in terms of recent publications. And again, I would say that we are interested, but my group is currently doesn't have all the resources to go into all of these fields that we are interested, basically. So that's the clear, let's say, short answer. But I think there is definitely room for bio-based, let's say, let's say, energy storage materials. I think that's very important field. So I think you are doing very nice research. Cellulose is obviously very good candidate.
Professor Mika, is it okay if I contact you for some proposal writing or something, so that it can be put?
Yeah, I will be always happy to receive, let's say, self-driven and ambitious researchers to contact, and yeah.
To some good funding agencies for collaborative research?
Yes, that has to be, of course, checked case by
Hello?
case, but yes, Avinash, the short answer is yes. You can contact me.
Yeah, thanks, Professor. Thanks.
Okay, thank you for all the questions. So I once again thank Professor Mika for the excellent presentation and sharing the knowledge with all of us.
Thank you, Sudha. And I think it was a very pleasant and nice opportunity to interact. So thank you so much.
Thank you. And there is few advertisement for the upcoming webinar. So the next webinar is about Lignin, about Lignin for packaging application. So if you are already interested and registered, and I'll welcome you all for the upcoming webinars. And thank you everyone for participating in the webinar series. Thank you once again. See you on coming webinar. Thank you. Bye.